Today's topic is defining severe service valves, led by CGIS Chairman Ross Waters. CGIS is a global supplier of the highest performance valves, controls, and automation. With more than 40 years of experience, Ross specializes in severe service applications and solutions. He is a voting member of ASTM on the GO4 Gaseous Oxygen Committee, serves on the Manufacturers Standardization Society as a task force member on the C114 steel valves and C409 knife gates, and has patented multi-phase meter technology. Currently, Ross is committed to publishing a new standard practice on severe service valves and has traveled to more than 140 countries while sharing his expertise in solving complex industrial problems. In today's session, we will discuss the importance of establishing the benchmark and rating system to identify what constitutes a severe service valve, how it differs from general purpose and fit for purpose valves, and the objective criteria required to identify severe service applications. You'll learn why such a definition allows clients to benefit from improved process performance, increased profitability, safety, and environmental protection. And with that, I will turn this over to Ross.
Really, thank you very much, and thank you, Valve Technologies, for this opportunity to present. It's something that I've been involved with most of my life. I'm 67 years old this year. I really started as an 11-year-old as a part-time kid in the same industry. So it's a long journey, and part of what we're going to talk about today is that, in fact, that journey. So as Julie said, we're been in business as ourselves for a long time. We practice what we do in a lot of different countries. We started as our own company in 1980, but it was split off from an existing company that got formed in 1965. So really just a continuous run of many years. And the fact that we're still here, I think, does say something about that we've got some things right. Like when we started in 1980, we were pretty limited in our business. We had really the only business in British Columbia at that time, Canada's Western province, was pulp and paper, and it was craft pulp and paper, which is the more challenging method of manufacturing. A lot of what we learned along the way was just from that industry. But as it declined, we saw that we had to move and get elsewhere. So today we are 10 offices throughout Canada and Australia, and we have maintained a record of what we have internally called severe service valves, and have sold over 48,000 of them to a lot of different industrial applications. As Julie said, I'm trying to share what I've learned and try to bring some new things to industry. And the MSS has given me this platform, as ASTM. And I think it's very important that as we grow older in this industry, that we find opportunities to give back to it. So really, what am I? I'm a person who loves valve. I got involved in it, as I said, really early. I've had some really good people in my life help me. The people on the left, that's Adams, very interesting company from Germany and Houston, Texas. And one of the people you see on the right is actually a Valve Technologies distributor too in Australia, a very good personal friend of mine, Phil Brannigan, where we worked in Australia on the cutting edge of an industry called hydrometallurgy. All of these things went into what is going to be evolving from this presentation. So I'm hoping today the presentation will give you a bit of a background in the history, show you why it should be useful, show the other classifications that other than severe service valves, explain where I think we're headed, and then give you some key factors for selecting these things if we all agree that they're necessary. The perspective I'm going to send over today is from my life as a salesman. That's how I look at all this. So I am a salesman, and even though I have this title of a chairman, that's not what I do. I've always been in business development, and the sales is what attracts me. I think I'm a good one, not in the sense that I'm successful at selling, although I guess I am in a way, but I do it from a perspective of trying to look out for the benefit of the customer. It's like I'm spending my own money and making sure that what I buy is the right thing. part of my DNA is this thing called fairness, which itself is very subjective. I detest losing orders when I find it's not fair. And that's one of the drivers of defining severe service for me. I can tell you that I've learned that there are no bad valves in the world. There are valves that are put in the wrong places and they fail. Just as that, there is no perfect valve. Every valve has an Achilles heel. Now, I can tell you I am a very huge fan of valve technology because I know what it can do. And its design is one of the closest you can get to perfection. But still, it's not perfect. There is no perfect valve. So we always have to try to find what is the right application, valve for the application. And on top of all of that, we have this thing called language. When we're talking about the same language, English, we have a challenging time to be able to confirm that what the idea being presented is understood from the people that are listening. So language must be really focused on to make sure that we get the right thing from that language that we're listening to. So here, for those you can see clearly, there is a valve, picture of a valve. This is a very good manufacturer of a valve. There's a really important piece of what I found here, and the story for this slide, is that people misunderstood what the difference between 300 PSI and class 300 or ASME 300. And this is in part, again, why this fairness thing kicked off in me. I bid to the specification, which was clearly class 300, 740 PSI rating, 50 bars. I bid and lost. And when I lost, I was very, well, first of all, surprised because I figured that we were one of the world's leaders at this type of application in valve, and didn't know who won until a year or two later. And I went to this mine in Chile and found out here's the winner. And then I realized why he won. He won because he passed the technical portal that said this meets the spec, and his price was lower. Well, of course it would be lower. His valve was rated to 300 PSI, and mine was 740. So that was another sort of direction and arrow that got us to where we're going. Defining severe service valves, then defining fit for purpose valves, and then defining general purpose valves. I want to just stop you there for 1 second and just have you visualize these three different criticalities. When I proposed this back in 2014, I didn't use those words. I used severe service valves at the very top, the most important valve. But in the middle of the three categories, I proposed general purpose. And for the bottom, I proposed commodity. The explanation, I think, will come along the way. So today, I can't use that three different ways of describing it. I have to use these three, and I'll explain as we go. And the communication about how this is done. So I want to make sure that we're all clear on there's a very big difference between subjective terms and objective terms. When I grew up in the very early stages of my career, I learned language like high performance, tight shutoff. They sound good. They sound important. They are important in a way, but they're subjective. They don't have any way to really measure. How high is high? How warm is warm? Those things need to be put into a place where we can have a third party agree that what that measure is correct. So we have these things in our lifetime called value, and we have these things called cost and price. And when we're trying to compare the cost to buy something versus what the value of it when it's actually in use, then we have a big difference. And for me, I've always been somebody who's wanted to focus on the cost of ownership. And then I look at things like different technologies about valves, not Valve Technologies, the company, but technology about valves. Because as I mentioned before, there's no perfect valve, and each valve type has its places for us to go. So valves for all of us may be, brand new in the industry, or some of us like me been in there forever. We all have a different way of looking at valves. But I think all of us in the world will look at cars in a very similar way. So I'm going to use these three slides just for a minute to give you some more ideas about communication. Here I'm asking you to choose which of these three cars is the right one for you to buy for your needs. I'm giving you some data. I give you 5 pieces of information. The problem here, though, is this information I'm giving you isn't enough for you to make an intelligent selection. So I'm going to give you some more information. Now, some of you may look at that and say, okay, that's what I need. I want to win a rally in a race. So I'm going to buy that one on the right-hand side. Some of you are saying, no, I want this for my family vehicle. So you're going to buy the one that has the most economical fuel rates. That's the one on the left. And when I finally give you the last bit of information, how much it costs to buy, then you can make a better solution and choose what's best for the application. For valves, this is similar, and yet I can show you, and I'm going to show you, where we don't get the proper information, so you can't make proper selection. Starting at the very beginning, though, let's think of all valves, no matter what they look like, what they do, they only function in 2 primary ways. They control, valve on the left, or they isolate, valve on the right. In both of these cases, very well-made valves fail to perform. So let's see why we think we can figure that out. Do control valves really control? And if yes, how long and how well? Do isolation valves really isolate? If yes, how long and how well? What about when the applications are very challenging? How do you arm the valve to survive? Do we need a different way of looking at severe service from general purpose? I believe we do. In 1995, I had been playing salesman at this Cominco refinery, a metals refinery that is 100 years old. In a long time of being in business, they developed a lot of habits. They bought a lot of historical products. They had 23 different ways of making metal, refining metal, with different processes that required different types of valves. But in the 100 years that they were there, they had a lot of baggage. They had a lot of older technology. We got an opportunity in 1995 to really help them modernize the way they used valves and analyzed valves. We had a trust with them. We got an order, a 5-year order, to help them modernize their plants by using the proper valve. And this slide's a little rough to read, perhaps, but what it was, as we showed them that again, this language that I'm using then was the commodity, general purpose, and the severe service. We improved their revenue by giving them more severe service valves where they were required and reducing the commodity valves where they were used, so that over years they benefited greatly. This was a good education for us and a very profitable education for Teck in those days. So if you looked at the actual revenue, we made more revenue ourselves, 4.9 million on converting them to severe service valves, and much less in the commodities. It was good for our company, but it was much better for Teck. They saved a tremendous amount of money buying less annually and having more runtime in their operations. So the journey started back then. It continued to go, this journey to what is a severe service valve. I started to decide to write some papers. In 2014, I actually wrote my first paper on defining what severe service valves were. That was the start of that. And from there, I decided that this is something that's going to be valuable, I hope. And I tried to attract the attention of the industry. What happened was MSS, which I had joined a few years earlier, mostly for the knife gate valve standards that were in those days really poor, and we needed to create a new one. They were eager and open to improvements in their industry. So I asked them, would they be interested in this topic? And they said yes. What I also would like everybody to realize, this is a great company society to grow. And if you're interested, please join it. They are pretty low cost to be a member. And you get a great deal of value, and you can participate in our industry for the benefit of everybody. So right now, there's currently 60 standard practices in update. Their mandate is to update them every 4 years. I can tell you that for those of you that are in the knife gate valve business, The original knife gate, MSS SP81, made in 1960, it was surpassed by MSS 135 in 2010. We're now in the 4th edition of that one, and it's grown from class 150 through class 600 knife gate valves. So it's been an expansion. There's 17 active projects right now, including severe service valves, defining them, and a new special high pressure gas test. And in 2017, they joined with ANSI to jointly submit these units. In 2016, they officially gave us the permission to go ahead, and we got a team of 14 people together, members from different companies, to do the task force. Now, that's 2016, and today is 2020, and it gives some idea about the complexity of this subject, perhaps, that we're not there yet. We started with a work number, PN 16-20, and we took a vote on those days, and we decided that this was the title that was acceptable, severe service valve. We had no negatives, and that's very important because you cannot publish a standard with any negative. They have to be resolved. So here's the start, the official start, in May 11, 2016. Now, today, I'm still waiting to publish it because we have, since then, one negative vote that we are unable to convince to change. This is an internal issue that we're trying to wrestle with, but it is a bit frustrating that it's taking this long to do something that everybody else in the NSS thinks is a good thing. I do accept that the negative vote has some validity, but it should be resolved because it's good for the industry. So there was a purpose. Again, in the early days, it was defining just severe service valves, and then it's grown, and we're trying to get to a point now where we can define not only severe service valves, but the other categories. We agreed with measurements on what a control valve, severe service valve, looks like. There is very clear evidence that if you have a certain condition, like cavitation, for example, that is definitely severe and it has consequences. The challenge that has taken us this long to get for isolation valves is that there is no single clear threshold for which you can say yay or nay. What we've had to do is come up with a multiple threshold score, and that's where we're at today. We will show you what that looks like in a minute. From my perspective, and this is again really from our company's world and probably very similar to valve technology, there are severe service valves in 3 different categories, although check valves are not really a secondary part of isolation control. They're somewhere in the hybrid side. But isolation valves, definitely. Control valves, definitely. Now we're trying to put them into severe service, fit for purpose, or general purpose applications. Give those guidances on why that happens and why it's important. If you look at the characteristics of general purpose valve, they're typically not consequential if they fail. They shouldn't be if they do. You look at things about a leak rate. Is it important? Is it critical? If it's important, they shouldn't be used. Do you need to have a lot of process data? Not necessarily. Really, you're buying a commodity. The purchase price is low, availability should be from stock, and you're not likely going to be repaired, you're just going to replace it. Little harder and more important category would be the fit for purpose, where the consequence of failure is higher. The leakage acceptability may be unique tighter. Your purchase price is not the lowest thing in the world because it has value and you're going to be able to amortize that cost. It's likely still to be stocked, but maybe not everywhere. And it may start to become cost effective to repair it. A severe service valve is one where if it fails, there's a serious consequence. The consequences that I'm going to highlight mostly are loss of business opportunity, the loss of your income stream, loss of the money that you have to do to repay that replacement. What you want for isolation valves is the long-term isolation ability, and you want it to be tightened believe me, I'm going to explain what tight means in a different way in a minute. Because again, tight is very, very subjective. I want to make it objective, and we can. We need a lot more information. And this is one of the key areas that I want to get across, is that information that we need to have more of is for us to make better selections of where we're at. The typical purchase price is going to be more. But again, if it works for your application, the actual cost of ownership should be low. We have to make the right match to it. Availability, it's not likely to be stocked, although the more of us who focus on severe service valves are more willing to put in inventory that is in stock. But often it's a made-to-order recipe. And you should likely repair it because it is an asset. So what we did is we came up, as I mentioned, it's very challenging to come up with a single threshold. We came up with a checklist and a score sheet. And I have, by the way, used this myself for the last year or so. And it's getting to a point where it's got a high degree of sense. It's starting to work. I don't think personally that we're actually there yet, because this is the starting point of our journey. We will have input from the industry where we need to change these values and come up with something different. But the idea makes a lot of sense. So under 20 on a total score, you're likely to be able to use a general purpose valve. Between 20 and 50, more likely to use a fit for purpose. And above 50, then you need to have a severe service valve. So this starting point gives us the objectivity that we want to include the fairness factor, or having more people see the world from the same lens instead of eyes. So what happened from the beginning in 2016 when it was defining severe service valves, we are now through the draft, I don't know how many drafts, it says draft 5C, but it's probably draft 20. The title and scope have changed to guidelines for classifying severity of valve service conditions. This is a big change, and in MSS, any change in the scope and title means you've got to go back to the drawing board and have to revote. And that may be one of the reasons it's taken so long to get this thing across the board. So again, as I mentioned, valves only do two things. Let's go out and have a look at some of the details that come about this. So whatever industry we're in, there are applications in there that should or benefit from using severe service valves. Some industries actually have a much higher percentage of severe service valves in general purpose. You can compare a refinery to a wastewater treatment plant. You're going to have way more SSIVs in a refinery than you are in a wastewater treatment plant. But a wastewater treatment plant also requires a valve to do something that is challenging for most valves to do. So even there, we will have a place for an SSIV, just a lower percentage. So in my opinion, and this is an opinion, not fact, but I believe from what I've seen, severe service valve, isolated valves are not gate globe or checks that are made to those specifications. I've never seen a wedge gate valve isolate as well as other valve technologies. So it's an industrial revolution invention. It's time to be retired to that bottom rung. I probably am going to offend a few people who sell that, but that's my opinion. Soft-seated centric butterfly valves, like the old Keystones or Grays, they are not, in my opinion, a severe service candidate. They may go into the middle section. SB81 knife gate valves, the original knife gate valves, they just cannot isolate properly. So they cannot be severe service isolated valves. And pinch valves are in that same realm. What I think they are is true metal seated ball valves, and I use that word true to define the type of valve that the valve technology's B11 is, a valve that was specifically designed with a metal seat in mind, rather than a soft seated valve, removing the soft seats and putting in stellite or some other metal seat there to make it a metal seated valve. That's not a true design metal seated valve that uses metal seats to isolate. It is just a change of seats in a floating ball valve. Triple offsets, guided shear gates, which is a passion of mine, and you'll see why in a minute, because I'm very involved with this type of valve. And the parallel slide gate, again, this is the valve technology ISO gate. It's quite different from the 100-year-old valve that was designed as a parallel slide again, back in the Industrial Revolution. And the word check valve engineered is because check valves, like control valves, should be sized for the flow, not for the size of the pipe. That's one of the biggest reasons why check valves fail. They're put in pipe size. And there are plug valves, sleeve line, and that meet this terminology. So one of the things that I want people to think about when it comes to isolation valves is the life history of that valve when it is doing its job. And isolation valves are kind of unique in that they have 4 different states of life. They're either fully closed, they're fully open, or they're cycling between those 2 states. And this has led me to understand the importance of knowing more about the valves that I'm trying to solve in isolation conditions when I don't know how many cycles I'm going to be expected to live through. I don't know when I'm starting as an open or closed valve. I don't know what happens to the dynamic state if the flow is moving while I'm closing or opening. Without knowing that, I can't hope to make a good solution. The control valve side of business gives that inherently because we're solving for flows that are continuous. Here I've got 2 static basic conditions and 2 dynamic. So I need all that data, which is more challenging than you might expect in the beginning. Corrosion allowance, there is a very important component on how well and long do the primary sealing components of my valve, whatever it might be, a ball in its seat, a butterfly in its seat, a gate valve, a knife gate valve. What is that corrosion allowance so that when I'm in service after a period of time, I still have the integrity of those sealing surfaces to give me the isolation I want. So here are what we're looking at. This is the true metal seated valve that I've grown up with. Part of where I am today is because of valve technologies. I really think Kevin Hunt was a master magician in bringing a concept of the integral seat from a different valve into the ball valve, and having at that time of his life the ability to coat it with carbides was a great gift to the world. This is the finest isolation valve in the world, in my opinion. I also have a great respect for the triple offset. This was designed and patented in 1960. I really trust it to do its job. This is Adam's invention. And what I like about it is if you look at this carefully, it's very careful to understand that they have different isolation abilities based on the amount of torque you give to this valve. So if you look at the bottom, if you only give 65% of the closing torque, it's not as tight as I would like it to be if I'm on steam. Class 4, that's failure in my opinion. Class 5, that's failure in my opinion. It's allowable leakage. As soon as you get to 80% universal tightness, then you get, in one direction, 0 leakage. The Germans, which this company is, use tightness, perfect tightness, is the same way I say 0 leakage. And if you do for bidirectional, you do 100% of the torque required, 72,000 inch-pounds on that valve, you'll get bidirectional 0 leakage. That's objective. That is not saying tight. That's saying, wow, that's measurable. The guided shear gate, as I mentioned, is a very close to my heart type of valve. I sell a lot of these globally. This is, again, a 1960 original patent, but it's been improved in 2017 to be a much different animal than it was in the past. And it's able to cycle and close and isolate perfectly, 0 leakage in dirty, disgusting applications. And if we have time today, I want you to look at this picture, and anybody can tell me there's 2 very wrong things about that valve. So have a look, think about it, and we can talk about it. So let's go look at general purpose. Why is it general purpose? Because the fluid is easy, water. If you look at the velocity, it's not very quick for control valve. So this doesn't require a special design. If you look at a severe service control valve, it's much different. Here's the process fluid, it's the slurry, the sulfuric acid, and it's really moving. Look at the feet per second, 923 feet per second of a slurry. That's a challenge. And the same thing in the ball valve. Here is a very challenging ball valve in the mining industry and hydrometallurgy. And the requirement here is something that came about in the industry maybe about 15, 20 years ago in this industry, the so-called thing called zero leakage bidirectional. I wanted to know, what does that mean? How do I test? If I'm metal seated, give me a test that requires zero leakage. I don't think there is one. Valve Technologies has one. That's an internal company. You look at some of these other things that give you clues. Look at the fluid here. In this case, size of solid 64 millimeters. So in inches, that's about 2.5 inches. Look at the velocity. The velocity is going 4.5 meters per second, 16 feet per second. I can tell you that's a challenge. But what really makes this challenging in this specification is the frequency of operation. Once per week. Once per week, that valve has to close against that flowing velocity, 16 feet per second, which doesn't stay 16 feet per second as you're closing. It accelerates. And it accelerates with 32%, or sorry, 58% minerals that are up to 2.5 inches long. That's a challenge. So what we do is we look at all of these applications and we say, which is the best technology, best available isolation technology? Here I'm also always going to come back to Valve Technologies has an incredibly good way of being able to solve that isolation, the so-called best zero leakage, total isolation. But here's not only closing fluid from upstream to downstream, I don't want to have any zero huge emissions. I want zero there. I don't want any body joints. I don't want anything from inside going to out. That's the best technology. When things aren't perfectly tight, bad things happen. Here is the picture on the right, a valve that cost to buy $300,000 and lasted 17 weeks because it started to leak. And as soon as it started to leak, the differential pressure, which is the enemy, and the fluid, which is the slurry, made that valve fail very quickly, and they lost the payment of their system. So there's lots of bad things happen when you choose the wrong technology and it fails. And some of these are going to be part of where I'm going to use you, give you some better examples. Here's a picture of 5 different types of knife gate valves. All of them are knife gate valves, but they all function differently. And it's this misunderstanding of how they function that causes issues. The picture on the left is a brand new picture installed. It's a push-through knife gate valve. Nothing wrong with the push-through knife gate valve except that it pushes through process. And that process that's dropped on the bottom is a problem if it's acidic. In this case, it's neutral, so it's really only housekeeping. The picture in the middle is interesting for me is that to solve the problem, we have to put a 22-inch bore cylinder on a 10-inch valve to have the horsepower closing strength to close against what was inside that pipeline. A lot of scale. The one on the right is that liquid leaking is acid. That's not a good thing. It was done, chosen for the wrong reason. Here's a conventional knife gate valve. It leaked, and because it leaked, it allowed the process that was pregnant to precipitate and become a clog for the valve to operate. This valve, very well made by a reputable manufacturer, failed because it had a leak rate far higher than what was necessary for the containment of what's inside it, which is just water. And here that leakage made an iceberg, which sealed the valve and wouldn't drain the tank if it was required to drain. This picture is one for me, it's important. You know, when I looked at the data sheet to supply the valve, the data, the fluid was brine. Well, that brine was saturated with solids. And what they did is they precipitated out as a solid inside the pipe. That's what's going to happen inside the valve as well. So if you don't factor in the extra drag or the presence of solids, you're going to have a hard time solving the problem. I love to look at things from a different lens. Here I see a specification by a reputable engineering company that chose Clarkson KGD, a very good valve for mining. But is this mining? Look at the gate, titanium grade 2 gate material. What mining would use that? And look at the body, ductile iron, coated internal and external. I think there's a pretty big difference in the corrosion resistance between ductile iron and titanium. And if I need titanium and EPDM to save my body, then I better make sure that the valve doesn't have external issues. So this one was built for a project which I knew would fail, because they didn't understand what this valve did. What they actually bought was similar. They bought different manufacturers, but they bought from another reputable company, ITP Engineered Valves, and they installed it with a carbon steel body, not so obviously lined so that it was protected. But here's what happened. In a very quick time, external corrosion ate the body from outside in. And that titanium gate and the Teflon seat were okay, but the valve failed, and that money that was spent was completely wasted. Here, the same engineering company didn't learn from his past and put in the same types of valves in another facility where we're watching acid pour out of that valve when the valve is open. And what was the consequence? Autoclave 1 and autoclave 2 had to be idled, and the idling cost them $134,000 an hour of lost profit because this valve was discharged. At the same place, the same valves did it on line. So not only an acid in line, it's not the valve's fault, it's the guy who picked that. This cost 5.5 hours. They had to isolate different pumps. 5.5 hours at $134,000 means the cost of the valve is irrelevant. So we're getting to where I think we need to focus. And I don't believe that SSVs are always the right valve for the application. There is a place for general purpose and a fit for purpose. We need to understand where they should be. So what's very important to understand is the number of cycles, the differential pressure that's happening, because it's differential pressure who's trying to make the leak happen. The solids, are they in suspension? Are they in solution? Are they both? Is it a pregnant solution that when it stops, it can no longer hold the solid in solution? Is the product resistant to corrosion? Okay, the titanium and the EPDM in the past slide was, but the ductile iron or carbon steel wasn't. And then temperature and abrasion and erosion. I just like using that slide on the right there, the iso corrosion chart for sulfuric acid. To me, it's a really interesting problem. If you're using sulfuric acid in your process, and you're adding other parts for both, you're dewatering, you're adding water or different chemicals, the concentration of the H2S changes, obviously. Look at what metals work and don't work. Stainless steel works on low pressure, low concentration acid, as it does at the high end, 93%. Ductile cast iron, WCB, BCFN are fine at the very high strength, but limited area. But in between, you got to use Haskell, super duplex, a whole bunch of other materials, and they change from temperature and concentration. We have learned ourselves internally that the application will always drive you to what is the right valve technology. And I think it's always best, obviously, for the long term, that you choose the best valve and criticality for that duty. All three are going to be needed at some point. Paying the appropriate price is always the best. Not every application requires it, we accept, but I do think that it's important to know where it makes a big difference. And on top of all of that, one thing I've learned on the severe service side of things, you really need to pay attention to servicing and commissioning. This slide is illustrative of trying to do the right thing, but understanding the world's a complex and difficult place. This picture is one of 35 titanium check valves in Madagascar. We sent the valves with IOMs printed in English, French, and Malagasy, the three languages that are spoken at Madagascar, so that whoever installed them will install them correct. This one of 35 is installed correctly. I can see the arrows in the right direction. I can see the word top on there. But the reality was 22 of the 35 were installed upside down. And that affected how they survived. So for us, we really need to understand that sometimes you've got to spend a little bit more to get that servicing and commissioning. So we've learned a few things. We've learned that application details are really critical. There isn't one size that fits all. There's always going to be likely an engineered unique situation where you have to have that ability to see what's necessary. What is that normal starting position for an isolation valve? Open or closed? They're different. How many times during the required cycle life will that valve be required to do that? What is the minimum time it has to perform? over this. And what is that performance? You know, we use the words in North America very loosely. If you look at a lot of specs, they quote class 4, class 5, class 6. Does everybody realize that the title of the standard that comes from is the allowable leakage rate of control valve? Why are we using it to define what isolation valves are? I just don't think. I think you all can expect that we need a higher safety margin for actuation, and we need to have very specific options for these applications. For me, it's very important because now it levels the playing field. I won't lose an order if it's done this way to somebody who didn't understand that 300 psi is not class 300 and quoted a valve that didn't work. That money was completely wasted. So there's a fairness equivalent there. And then we get a chance to be more successful, both for us and the end user, who is really the person that we need to do analysis. So let's spend more time up front, really understanding what the process guys who design these things and the operators who will operate them really need and want from the thing. Get that detail, get it all up front in the beginning so we can be competitive fairly to everybody else that's there, because we're not trying to eliminate everybody. It's got to be a situation where you feel that there's going to be some competition, because that helps drive us. Use some new tools. There are some things like better testing. And the API 598's good test, but is it valid for all applications? You know, it's only done for 15 seconds to 3 minutes, 5 minutes, using a benign fluid, air, water. Is that valid when you're talking about superheated steam? I don't know. I don't think so. And in the future, there will be more data coming, so we'll know what's happening to valves. One thing I have definitely learned in the last little while is that operators don't necessarily operate the valves that we supply them in the way that we think that they're supposed to be operated. And with the intelligence that's available through the internet these days, IoT, we're going to gather that data that will help us push this even farther. So let's understand that for sure, many industries, 1 year is not enough, but in a lot of places that what I go through in hydromet, there's not a hydromet plant in the world, there's 70 of them, that can guarantee they can go a year without a valve failure. Not a single one. And we've been practicing some of this stuff for 50 years. There's one plant in Australia, Murrin, that started up in 1998. It has not reached nameplate after all these years, and it's because of valve fault. We need to make sure that the corrosion allowance are much, much tighter than the pipe they're involved in. You got to make sure that the actuators have significantly higher output, because in severe service, often things change. You start with a nice sweet fluid, and at the end of the day, you got 2 inches of pipeline ID from the solid precipitation. There's a lot of different things happening in your operation, and you've got to consider those, static and dynamic. And while CapEx is really critical, we got to be able to balance it with what it costs you to own this. Experience does count. I think it's foolish for companies to go to pipe, valve, and fitting companies that are in the Walmart side of the business and expect to have a really great solution on a severe service. It costs too much money to be in the severe service business. You need a different set of people, a different set of manufacturers. It's likely that you're not going to get the same result. Never try and put a control valve in an isolation application or vice versa. They're just not designed to do both. And of course, learn from the past. This last slide, I don't know, life is one of those weird things. This is a picture from a mine in Chile that thought they would save money on a 24-inch valve for an application that was originally installed with a solid titanium butterfly. It sold for $60 grand in 1995. So in 1995, these $60,000 titanium butterflies were installed, and today they're still there, all these years later. In 1997, I got an opportunity to go to the plant, and they had a little brownfield additional project, and they balked at adding a new 24-inch valve at $60 grand. They said, I can buy this for $3,500. So they did. They bought a ductile iron body, EPDM-C, with a little PVDF plastic lined ductile iron disc. What you can see there is a bit of the lining left over. That valve lasted literally less than 7 days. So $3,500 times how many times that is in a year, 7 days, that's a lot right now, times 25 years is a lot more money than 60 grand. You've got to buy the appropriate technology. That's it.
Perfect. Thank you so much, Ross. We appreciate the information.